Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WAEC, JCE, KCPE, IJMB, JUPEB, KCPE, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Hello, welcome to physics class, and today we are going to be talking about heat energy. By the end of this lesson, you should be able to differentiate between heat and temperature, define quantity of heat of a body and its relation, define heat capacity and specific heat capacity, solve problems relating to heat capacity and specific heat capacity. If you are ready, get set and let's get started. You see, when we talk about heat energy, many people make this mistake of comparing it to temperature. Heat is quite different from temperature. They are not the same. So in this class, we really talk about, that is why I brought that as one of the first specific objectives, so that as you are watching me at this time, watching this video, you will be able to find a thin ground between that heat and temperature. However, remember that heat is just that which transfers. If you are watching this, you now see that this wasn't all the molecules as we are trying to imagine. Look at, it's blue at the end, it's blue, but then you see what happened. Then it starts getting red hot until it gets to the end. Everywhere becomes red. That is exactly what heat does. Heat travels between the molecules and then from one point to the other, especially from hot part to another. So the heat, I also want you to know on this part of introduction is that when we are talking about just heat, we are not just talking about the heat given out. We are also talking about heat taken and also heat given out. Also remember that everybody has heat. When I mean body, I'm not talking about human beings. I am talking about objects, because that's what physics mainly learns or teaches. So everybody has a quantity of heat. Even the ice block you have has a quantity of heat in them. All right? So let's keep moving as we unveil the concept. Now, the first thing I want us to talk about is heat and temperature. Like I was saying, now let me define that heat is a kind of energy which is always on transit or travels from a hotter body to a cooler body due to difference in temperature. So if I have a body, let's say this body is having 50 degrees Celsius, and then I have another body in contact with this body and having a temperature of 30 degrees Celsius. You know what will happen? Heat is going to transfer from the hotter body to the cooler body. Why is heat on transit? Because that was the first thing I said. I said that it's a form of energy on transit. Why is it on transit? It is only going in order to attain equilibrium or thermal equilibrium. Now, another name for heat is thermal. So the difference temperature, it moves just like what you have here on the screen. You see, this is warmer object and this is the cooler object. What happened? Heat moves. That is what heat does. Anywhere there is a cooler body and a hotter body, the heat will be transferred to it. So heat is mainly of transference and is a part of energy. But when we talk about temperature, we are talking about the average internal energy, the average kinetic energy of the molecules in a body. I said the average kinetic energy. So if I have this body now, and each of these and everything that make up this body, are the molecules that make up this body, then each kinetic energy of the individual molecule that make up this whole body, the average of those kinetic energy is what temperature is talking about. But then the common definition that you know is that temperature is the degree of hotness or coldness of a body. So from this, you know that temperature and heat are not the same thing. Now, when we talk about the quantity of heat, let's look at it here. When we talk about quantity of heat, we are talking about the amount of heat a body can retain or can give out. Yes, because for you to, as much as you can give out, as much as you can retain, depends on the much you can give out. So we have this Q to represent quantity of heat. So this is giving us quantity of heat. So it's giving us Q. Now remember, we have quantity of electricity and other quantities, but this one quantity of heat, and it is measured in joule. Every energy is measured in joule. Now we said that this quantity of heat increases with mass of the body. That means the more the mass of a body, the more the quantity of heat that the body can be able to retain or to take. Then we also say that the quantity of heat of a body depends on the temperature change. What do I mean by temperature change? Sometimes we can give temperature change as saying θ2 minus θ1, you know? What I mean by theta is just the temperature of a body, initial temperature and the final temperature. Just look at what I mean by that. Having this, if you look at this one, let's assume this is 0, 1, and 2. You say that probably this is 2 degrees Celsius. That is the temperature for this one, where the hotter body has 0, 1, 2, 3, 4, 5. This is 5 degrees Celsius. So you see, 2 of them have different temperature. So if you want to find the change in temperature, we're just going to say the 5 minus the 2. So that is what we mean by change in temperature. So what we are saying is that the quantity of heat a body is going to retain depends on the temperature change. So if the temperature change is like 100, it's going to have more quantity of heat. Then another thing that defines the quantity of heat of a body is this nature of the material. For example, you can't compare the quantity of heat absorbed by water to that of maybe iron or copper, because water retains much quantity of heat than most of those metals, and that will be seen in their capacity, specific heat capacity, and all the rest of them. So if you can be able to apply your mathematical principle, this the first one, the first statement, second statement, and third statement, and then we now combine them by saying this is equal to m change in theta, all right? Remember that this is a constant, this c is a constant, and it varies from body to body. So if I do this, I'm going to say that this is equal to km change in theta, whereby k is the same thing as the c, because it's the constant of proportionality in this experiment or in this expression. So, and that is what gave birth to the equation you are seeing on the board. And that is what gave birth to this equation, where we say that the quantity of heat is given as mass of the body and the nature of the body, or given as specific heat capacity of the body and temperature change. And this is what we mean by the quantity of heat in a body. And now we have one example there to make up with. We said that the temperature of a piece of metal of mass 9 grams is raised from 10 degrees Celsius to 110 degrees Celsius when it absorbs 108 joules of heat energy. Determine the specific heat capacity of the metal in joules per kilogram per Kelvin. Now, we are going to solve them using this, our relation. So if you look at this, the formula is already there. So we now say that the quantity of heat is already given. The quantity of heat is given as 108 joules. Anytime you see that J there, you now know that it is energy. Now this is degrees Celsius. And somebody may say, why not use Kelvin? It doesn't really matter in this calculation. Whether it's Kelvin or degrees Celsius, you just use them to solve. Now, the mass of the body is given as 9 grams, and I have to convert it to kilogram. So I'm going to say 9 divided by 1,000, which is 0.123. So this is it, kilogram as the mass of the body. And then we are talking about change in temperature. So I am going to use theta 1 to be 10 degrees Celsius and theta 2 to be 110 degrees Celsius. So these are the expressions for this. Now what are we going to look, what are we looking for? We are looking for the nature of that metal. And the nature of the metal is mostly called specific heat capacity, and it is given as this C. So let us just plug in our parameters and see what we are going to have. So we are having, using Q is equal to MC change in theta. So we have 108 is equal to 0.009 times, I'm looking for C, times 110 minus 10. So you have 108 all over 9. Let me go with this. Then times C times 110 divided by this is going to be 100 over 1. So you see why I prefer to use this one. So we now have 0.9 C equal to 108. C is equal to so we are going to say that this is 108 divided by 0.9, which is 120. Remember that you need the unit. It said in joule per kilogram per Kelvin, and that is taken care of when I divided this by 1,000, is to bring it back to kilogram. And that is why we have this. It's going to be joule per kilogram and Kelvin. And this is the value of the nature of the metal used in this question. Now, we also have another one. It said, find the mass of a copper block with heat capacity 50 joules per kilogram, 50 joules per Kelvin. Now, this question is drawing us a little faster because we are going to look at what heat capacity is as a whole. However, we have that quantity of heat is equal to mass times specific capacity times change in temperature. Now, there is another quantity of heat which we call heat capacity. This heat capacity is given as I like to use HP for heat capacity. Different textbooks use different parameters for this. And that heat capacity is given as MC, you know? So it simply means that if I remove MC out from this equation, I replace it with MC, with HP, because MC is HP and HP is MC. So I can remove this and replace this with it. So I have that quantity of heat is equal to heat capacity times change in temperature. And that is the only way we can be able to deal with this question. So we have, okay. So they didn't give us this. So this is out of it. I will still go back to this equation. I'm going out with this one. I'm going to say that HP is equal to MC. So in this case, we say that the mass of the body is what we don't know. And they gave us specific heat capacity, and they gave us heat capacity. So heat capacity is under this place, which is given as 50. And the mass of the body is what we are looking for, I don't know, multiplied by the specific heat capacity, which is given as C, which is SHC, and which is 400. So M is equal to 50 divided by 400. This will cancel this, and this is 1/8 kilogram. So this is the mass of the body for this question. A copper rod of heat capacity 632 joules per kilogram is heated until its temperature. We'll come back to this question. Now, let's talk about heat capacity, even though I've given a little. Now, this is the quantity of heat. Heat capacity is defined as the quantity of heat needed to raise the temperature of an object by 1 Kelvin or 1 degree Celsius. So this is just what I did. Heat capacity is mass times specific heat capacity, and that is just what it is. So we are talking about the quantity of heat you need to increase the temperature of a body by 1 Kelvin. If this is a body, assuming this body is aluminum, or let's say copper, and it is 50 kg, for example, and this temperature, the temperature of the body at this point is, let's say, 50 degrees Celsius. Now we are asking you, what quantity of heat is needed to increase this the temperature of this body by just 51 degrees Celsius? So that quantity of heat needed to achieve this is what heat capacity is talking about. Let's just try to see if we can do this. But then we know that the specific heat capacity of copper is 50. Let's do this to find out the quantity of heat needed to achieve this. So I am looking at this now. So we said that the mass of the body is 50 kilogram, right? And then the temperature, the specific heat capacity C for copper is given as 400 joule per kilogram per Kelvin. This is another way you can write joule per kilogram per Kelvin. Then the change in temperature is going to be 1 degree Celsius or Kelvin. So let's find out. So we are going to say that quantity of heat is equal to, that heat capacity is equal to mass times this, M times specific capacity. So this is going to be 50 times 400. So HP is going to be, this is 20 joules. So you see that now. So that means about 20,000 quantity of heat is needed. So this is this per Kelvin. This is the quantity of heat needed to raise the temperature of 50 kilogram of copper from 50 degrees Celsius to 51 degrees Celsius. And that is the essence of this definition. Now, we have another one which is called specific heat capacity. Now, this is the quantity of heat required to raise the temperature of 1 kilogram mass of an object by 1 Kelvin. You see? So this particular specific heat capacity, just like the name entails, is more specific. It's centered only on a unit mass of the body. When we talk about the unit mass of the body, we are talking about just 1 kilogram of a body. For example, this is a copper of 50 kilogram. No, when we cut this particular copper of just 1 kilogram of this copper and start heating it, the amount of heat needed to raise the temperature from 50 degrees Celsius to just 1 degree Celsius is what specific heat capacity is all about. Now let's solve this question. Now we said that a copper rod of heat capacity, this is heated until its temperature changes from 38 to 98. Calculate the quantity of heat supplied to the rod, and if the specific capacity of the copper is 390 joules per kilogram per Kelvin. Find the mass of the rod. So in this question, heat capacity, HP, is given as 632 joules per kilogram. Now, change in temperature is 92 minus 38 degrees Celsius. And then we are looking for the quantity of heat. Remember, the formula for quantity of heat is given as MC change in theta. Now, like I was saying, also recall that HP, which is the heat capacity, is given as MC. So this quantity of heat is going to be HP change in temperature. So this is what we are going to do. So quantity of heat is equal to HP is 632 multiplied by change in temperature, which is 98 minus this. 12 into 8 is 4. This is 8, 54. So quantity of heat is going to be so 34,128 joules. This is the quantity of heat needed to raise the temperature from 38 to 92. Now, the second question says, if the specific heat capacity of copper is 390, find the mass of the rod. So C is 390 joules per kilogram per Kelvin. Now we are looking for the mass of the rod. I can use only this formula to find it. This formula can help me in this case because HP is already given as 632. So having 632 is equal to M times 390. Remember, this is the C, which is coming off from this relation. So I'm going to say that M is equal to 632 divided by 390. M is going to be, it's about 1.632 divided by 390. 1.6 kilogram. So this is the mass of the rod. Now, let's talk a little about latent heat, even though we are going to look at them fully on its own as a different topic. Now, latent heat of a body is the quantity of heat required to change the temperature of a body, required to change the state of a body without change in temperature. So, even though it was written without increasing the temperature, it could be whether increasing temperature or reducing temperature, provided that that quantity of heat is used in changing a state of a matter, then we say that we have a latent heat. Now, let me let you also know that when we are talking about latent heat, we're also talking about a quantity of heat. Now, remember there are different quantities of heat. The quantity of heat, which is the total one, which has this general formula, and another quantity of heat, which is also seen as heat capacity, which is given as MC. We have another quantity of heat, which is given as ML, which is latent heat. And that is given as H is equal to ML. This is another quantity of heat, which is called latent heat. However, there are different kinds of latent heat. We have latent heat of fusion, and we also have latent heat of vaporization. We are going to look at them one after the other. Now, we also have another one we call specific latent heat. So we said that specific latent heat of fusion, which is the quantity of heat needed to change a body from its liquid to solid or from solid to liquid without a change in temperature. But then remember, it is specific latent. So it is centered on a unit mass of the body. So the quantity of heat required to change the temperature of a unit mass of a substance from its solid to liquid without a change in temperature. So that is what it is all about. So this one, just like we treated specific heat capacity and heat capacity, we said that specific heat capacity is centered on a unit mass of the body. In the same way, latent heat is talking about change of state of a substance. But when we talk about specific latent heat, we are talking about the unit mass of a body, the quantity of heat needed to change the state of a unit mass of a body without a change in temperature. So we have specific latent heat of fusion. We also have specific latent heat of vaporization. Different questions are going to lead us and guide us to mastering each of these latent heats. Now, but then before we go, let's look at this kind of graph. You see this graph you're seeing here? I can term it as heating. So heating, a body was heated from a particular temperature until it gets to a particular temperature. This temperature you are seeing here is the temperature. Now, let me first point out these stages. You see the stage at this point where the thing is slant, it's just constant. It doesn't continue. At that point, we said there is a change of state. There's another change of state here at this point when it changes to gas. Let me do more illustration on the board. Now, I am going to use water, for example. Let's assume we have this. I'm talking about heating. When you are heating a body, what happens? Let's assume that this is 0 degrees Celsius. And let me use time and probably temperature. Yes, temperature. That is, I'm going to say degrees Celsius. So I'm going to say maybe time taken. Or I can also put quantity of heat here. So the more the heat is increasing. So I'm going to use Q, joules. That's my choice. Now, let's assume the body was at this point. So when you start heating the body, what happens? The temperature will start increasing. No, it can never do like this. Look at this. The temperature cannot do like this. Why? Because at 0 degrees Celsius, we are talking about change of state. Change of state happens in 2 stages. When it changes from solid to liquid and when it changes from liquid to gas. So at that first point, what will happen here? Remember the definition of latent heat, that at that time when there is a change of state, there is no change in temperature. So what happened at this point? It will continue going this way. So at this point, you have M, L, F, latent heat of fusion. So after some time or after a quantity of heat has been given, then what happened? It starts increasing. When it increases to a temperature which is 100 degrees Celsius, what happened? Another change of state will happen, and then it will be constant again, then before it takes off again. So this is what happens for a solid or for an ice or a block or a solid for water. So from here, 0 degrees Celsius, then water, then when it gets to there, this is steam. So at this point, when it is also constant again, we're going to call it latent heat of vaporization. But whenever there is a surge in increase, we are talking about change of temperature because it is from 0 degrees Celsius to 100 degrees Celsius. So I'm going to put this and this. More questions will guide us on how the principles are applied. Remember, this is for heating. For cooling, a different thing happens because for cooling, it's going to start from 100 degrees Celsius, then goes back to this and down. This is all you have to know about latent heat. Then there is also a kind of question that we have, and that is why I decided to include it here. Temperature difference in waterfall. So we are looking at, remember, there is a law of conservation of energy. So I decided to bring this question on temperature difference in waterfall. You said that a waterfall is 120 meters high calculate the change in temperature of a quantity of water that falls from the top to bottom of the waterfall, neglecting heat losses to the surrounding. Take G as 10 meters per second square and specific capacity as 42. This should be 4,200. So we are going to look at so in terms of this waterfall, it is just gotten from the fact that energy is neither created nor destroyed, but is converted from one form to the other. So from potential energy, because when we talk about waterfall, it's a function of height. And that is why this height is given at this point. And change in temperature is also there. And that is what we are looking for. So we are saying that potential difference, which is mgh, is equal to mc change in theta. You see that? So why do we do this? Why can we now relate the quantity of heat to potential energy? Because they are all energy, and energy is transformed from one form to the other. So we can have electrical energy converted to heat energy, which we're still going to do here. We can also convert from nuclear energy to any form of energy. Energy is neither destroyed nor created, but it's transformed from one form to the other. So in this case, I'm going to cancel mass because mathematically this is done, and G is 10 times height is given as 1260 is equal to, I don't know the change in temperature, but I know that specific capacity of water is 4200. Please, 4200 is the right word, is the right value for specific heat capacity of water. So even though that is 42, so this is the right thing to write. So what do we do? I'll cancel this 0, I'll cancel this 0, I'll cancel here, I'll cancel here. I have 26 is equal to change in temperature times 42. So we say that temperature is equal to 26 over 42. So this is 13 over 21 degrees Celsius. And that is what it is. Thank you. We have come to the end of this lesson. But before we go, we are going to take a few more exercises from Examguide app. Okay. We are in Examguide app, and this is UTME. We have the question here given. It says calculate the temperature when 500 grams of heat is supplied to 100 grams of water. Specific capacity of water is given as this. So there is a temperature change here when 500 joules of heat is supplied to of water. Then we are going to look at change in quantity of heat. The change in quantity of heat in this case is going to be equal to mass of the body, specific capacity of the body, and change in temperature. Now in this case, we are given specific capacity of the body, and that is 4,200. And then we have the change in temperature, which is 500 minus 100 is equal to mass. Mass of the body is not given, times specific capacity of the body, which is 4200 times change in temperature. All right, so the 100 there is the mass of the body. I was getting a little. So the mass of the body there is 100. So I'm going to convert it to 1,000, to convert it to kilogram, to be able to achieve it. So I will cancel this and this, cancel this and this. Then this will cancel this. I will have 500 is equal to 420 times change in temperature. So change in temperature is 500 divided by 420. So we have that change in temperature is 25 over 21, and that is going to be 1.19. So 1.19 is approximately 1.2, and that is option A. It said when two objects A and B are supplied with the same quantity of heat, the temperature change in A is obtained to be twice that of B. The mass of A half that of B. The ratio of the specific capacity of A to B is. Wow. Let's look at this question. Now, one thing you have to do is simple. We have to stick to the principle. No matter how big the question seems to be, I'm going to write the quantity of heat for A, and which is going to be mass of A, specific capacity of A, and change in temperature of A. That's the first one. Then I'm going to have quantity of B, of heat of B, and which is mass of B, specific capacity of B, and times change in temperature of B. Now, there are a few statements made there. They say that they have the same quantity of heat. Therefore, I'm going to say that quantity of heat for A is going to be quantity of heat for B. This is the first statement you are going to note. He said that when the two of them are supplied with the same quantity of heat, look at that area, same quantity of heat, the temperature of A is obtained to be twice that of B. So the change in temperature of A is going to be 2 times the change in temperature of B. This is another statement. So we're going to keep them as equation and use them to do substitution. One more thing they talked about the mass of tend to be twice that of B. Now, he said that the mass of A is half of B. So the mass of A is half times that of B. So this is another statement which is going to lead us to this. Now let's go back to the first one, which is the key. We are going to have that quantity of heat for A is equal to quantity of heat for B. So quantity of heat for A is given as this. So I'm going to say MA CA, change in temperature for A, which is equal to mass of B, specific capacity of the body B, and change in temperature of body B. Now look at this question. Look at this. They said that the mass of A is half of that of B. So instead of writing mass of A, I'm going to remove it. I will put mass of B over 2 times specific heat capacity of A times specific change in temperature of A, and change in temperature of A is given as 2 times change in temperature of B. I'm going to say 2 change in temperature of B is going to be equal to mass of the body of B, specific capacity of body of B times change in temperature of B. Now see, well, I'm going to cancel a lot of them. Mass of the body B is going to slash out mass of body B. Change in temperature of B is going to cancel, sorry, this is B, is going to cancel change in temperature of B. And look at this, 2 will cancel out 2. So everything we are seeing here is CA is going to be CB. Now what are we looking for? We are looking for the ratio of the specific heat, the ratio of the specific capacity of A to B. You don't even need to. This is 1 and this is 1. The ratio of A, CA over CB is going to be 1 over 1, which is 1:1. And that is given in option D. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell, and share the video to people that will benefit from it. Bye.